Okay, so let's go. So today we're going to look at the Carnot theorem and principles. So just to give you an idea, I think Carnot was born on 1824 in that time. All right. So why is this important? So first, Carnot is probably one of the fathers of thermodynamics. The reason is that we said that the first law of thermodynamics, Q minus work equal change of energy, has two limitations. One is that it assumes, so let's say for a cycle where this is 0, it was assuming that all the heat will be transformed into work or vice versa. So basically, the first law assumes that everything is 100% efficient. And the other thing is that this equal sign really cannot be gone in both directions. Okay, in some cases. The example I give is not 100%, but yes, you can have water that can go from ice to liquid, from liquid to ice, back and forth as many times as you want, but you cannot have a piece of log that you burn, you get ashes, and then get back the log from the ashes. So this is known as reversible or irreversible. Alright, so let's do some figures. So the general picture for, let's say for an engine, for a power cycle, we say was what? You have a hot reservoir, alright, that provides heat, and this can provide work. So basically the first law of thermodynamics, this is what it's indicating, is that all the heat can be transformed into work, or the work, again, if you go back and forth, could be transformed in the same amount of heat. However, we know that this is not possible, because any type of engine, can be in a refrigeration heat pump or power cycle, always operates between two temperature reservoirs. And we find out that for a power cycle, the efficiency is always whatever you're trying to get out, work, divided by whatever you need to put in this case heat. The amount of work you can get is always the difference between the hot reservoir and the cold reservoir divided by QH. So the general expression for the efficiency was 1 minus QC over QH. Okay? So in one of the previous videos, I showed that the efficiency for a Carnot cycle, this was equivalent to what? 1 minus TC over TH. So you see that Carnot already covered this first deficiency of the first principle of thermodynamics. He was able to find the efficiency of a Carnot cycle. So this would be for an ideal cycle or Carnot cycle. And this would be for a general cycle. Okay. So maybe let me add one figure. So what is the Carnot cycle that we used to derive that? If you remember, the Carnot cycle for the TV had to operate between two temperature reservoirs, so the hot and the cold. Okay, so that's why the change in energy here is 0, because you start from one point, you end up to the same point. And here you will have what? The Q hot, equivalent to this one here. And this would be here the Q cold. Okay, so this equation here is what is known as the Carnot theorem. Okay, so based on this information, Carnot stated two different principles. So will be Carnot Principles is what? So the second concern is reversible, irreversible. So on his first principle, he states that the efficiency of an irreversible heat engine, so this is the general one, is always less than the efficiency of a reversible heat engine operating between the same two temperature reservoirs. Okay, so basically you see Carnot solve this problem over here, but also this one here at the same time. Because basically what he's saying is that before the first law, we state that if I remove this, all the heat will be transformed into work, or the work into heat. But now actually what you can have is that this will always work. An engine or AC system or heat pump will always operate between two different temperature reservoirs, okay? And the efficiency will be equivalent to the ratio of the temperatures, one way or the other, for the refrigeration of the heat pump, and that will be a Carnot cycle, and the Carnot cycle is reversible. This one will not be reversible, so the efficiency needs to be a little bit lower than this one. So the maximum efficiency that a reversible cycle can obtain is given by the Carnot theorem. The general one is given by this expression over here. Okay? So basically that gives a new definition to reversible if you want. Reversible is within the Carnot cycle if you can come back to the initial state from the other state. Would that affect, basically, at the end you need to have the same QH, Q cold, and W when you go back and forth. Okay, this should be here, Q cold. All right, now let us write down the second Carnot principle, which is not that important. This one is important here, and actually this one in a more simplified way, you can just say that the efficiency of an irreversible cycle is always lower than the efficiency of a reversible cycle. So this equation is important. The second one is not that important, but conceptually it brings some good information. The second one is that the efficiency of all reversible heat engines operating between two temperature reservoirs is the same. Okay, so this is very useful when you have this type of system. Let's say you have a hot reservoir over here, and then you have a cold reservoir over here, and here you can have power cycle, or here refrigeration, or heat pump cycle. So let's say you have this, this will create work that will go into the other one, and then you could have this and this over here. Let's see, Q cold, Q hot, and it should be T hot, T cold. Okay, so basically this statement says that the efficiency of these two heat engines, can be power or refrigeration, okay, is the same because they both operate between the two temperature reservoirs. And also this figure here is important because if you see, if either one of these two is not an ideal Carnot cycle, this system cannot operate indefinitely. Okay, so the efficiency of this one is lower than this one. You're gonna, after a certain time, this cannot be reversible all the time. So in order for this to be reversible, it needs to satisfy the efficiency using this expression. Okay, so let me just give you a summary of the two equations that are extremely important over here. So the first one is this one. Tc over Th. Okay, so I will do that probably on a later video, but why is this equation important? Because if you can simplify this, you equate one to the other. What do you have? Q sub C over Q sub H equal T sub C over T sub H. Okay, so for the cycle, and the other equation is the efficiency of the irreversible, is the equation up here, would always be lower than the efficiency of a reversible cycle. Okay, so that will be all for this video, but on the next video I will be using this information in order to derive the Clausius theorem, which is extremely important for the second principle of thermodynamics. Thank you for your attention.